Heat treating. The process of heat treating steel is known as allotropic transformation quenching, or the acronym ATQ. Allotropy means the existence, especially in a solid state, of two or more crystalline or molecular structural forms of an element. So that means we are changing the crystalline or grain structure in steel from a BCC, bodied center cubic, to an FCC, face centered cubic. Then steel converts back to a BCC when cooled slowly back below 1330 degrees Fahrenheit. Steels to be heat treated should be free of machining oils, and for a more exact process, some applications plate the steel with copper to prevent decarburization, high temperature oxidation, and alloy depletion. In this chapter, we will discuss the different quenching methods. Heat treating, commonly performed in a furnace or an oven. A complete heat treating process is a recipe that can be simple or complex. The exact heat treatment process for an exotic alloy is often a trade secret, proprietary information, and is not shared. Look at figure 11.1 and 11.2 in your textbook. And it shows the different size furnaces. Now they're quite different than the ones that we have in our shop. These are for large pieces of work, large pieces of metal, and very expensive. Quenching. Quenching is a controlled cooling process that changes a metal's crystal structure. For hardening to occur, material must be heated through the transfer temperature range. Quench mediums vary, and they include water, brine, oil, air, molten salt, and sand. Each medium is unique in how it changes the crystal structure of the metal. And here we are back to the iron-carbon diagram. Remember to refer to the iron-carbon diagram to determine the transfer temperature ranges for the different steels. And again, this was back in Chapter 9 and Figure 9.7 in your textbook. And this heat treating chart, it shows the temperatures for the different desired properties in steel. And again, this is a common welding chart that is in most welding shops. And as the temperature rises, it tells you what the steel, the color of the steel, what that looks like. It has the red heat range, and then you get up into the white heat ranges until you finally get a liquid steel. And that can happen anywhere above 2,500 degrees. And it's important for the welder to know what that steel is looking like when they're heat treating it. And here's the 4 stages of quenching: vapor formation, vapor covering, vapor discharge, slow cooling stage. And we're going to talk about each one of these stages and what happens to that steel when this is going on with the material. So figure 11.5 in your textbook, it shows the 4 different stages when quenching. Number 1, the vapor formation stage, is when the metal just starts to cool when quenched, when we initially put it into the quenching medium. Number 2, the vapor covering stage, where bubbles form all around the metal. Number 3, vapor discharge stage, where the vapor film explodes around the metal. This is where the greatest amount of cooling takes place. And 4, the slow cooling stage is the last stage of the quenching process, where the steel is cooled to the touch. The vapor formation stage. The liquid making contact with the metal starts to boil as the heated metal is first plunged into the liquid. This forms an insulated coat of bubbles that slows down the cooling process. The vapor covering stage. The vapor blanket or film insulates the metal from the quenching medium. The metal will not cool quickly unless this insulating vapor film is removed. Soft spots, warping, and cracking may occur. The metal should be agitated as much as possible. The vapor covering can be removed by quickly agitating the metal in the quenching medium. If the film is allowed to insulate the metal, again, the soft spots and warpage and cracking can occur. What is the cooling medium during the vapor formation stage? What is the cooling medium? What is around the part? Air. Air, as in the form of bubbles, is insulating the steel. So air formed around the part, insulating it from the actual quenching medium. That is why it's important to agitate and do those figure eights I ask you to do whenever possible. And we'll look at these stages again. So you have a visual of the vapor formation stage, the vapor covering stage, and the vapor discharge stage. The cooling rate at this point is the highest of the process. Remember that. You're probably going to see it again. This point has been called water-biting steel because of the crackling of the steel and the quenching medium. It happens quickly and is distinguished by the cracking and sizzling sound of the discharge of the vapor. And again, we'll look at those stages again. And there's your discharge vapor and C. The slow cooling stage. No further vapor film is formed, and this is the gentlest of phases of the cooling process. This is also the most drastic drop in temperature. See figure 11.6 in your book. Here's figure 11.6 in your textbook, and it gives you the temperature on the graph on the left side and the different stages of the cooling sequence along the horizontal line. And you can see it happens really quick. We actually have a video that I'll show you next of students in a previous class that actually filmed their quenching technique. And here's the video of the students dropping their molten piece of metal. Actually, they're hanging onto it with pliers and placing it in the water. And so you can get a view of the vapor formation stage, the vapor covering stage, vapor discharge, and then the slow cooling stage, and see if you can identify those. You see the air bubbles that are trying to insulate the material, and I told them not to swish it around in figure eights, and just so we can look at the formation of the vapor covering stage, vapor formation stage, and the vapor discharge stage. You can see it exploding the scale off the outside of the steel. Once those bubbles stop forming, that would enter into the slow cooling stage, the last stage. Where it takes it basically, I guess, down from around 800 degrees, and cools it to the touch. And here's another example of that. You can see it's kind of an amazing explosion that blows off the scale off the end of that steel, which is pretty impressive. And this was done last year by the metallurgy students. It's pretty awesome. And one more. Did a nice slow-mo there, and And there you have it. Quenching mediums. Brine is commonly known as salt water. It contains 5 to 10% salt. It cools the material slightly faster than water. Water quenching is the most common medium due to cost and convenience. But because it has such a rapid cooling medium, internal stresses, distortions, and cracking can occur in the metal. Oil quenching is gentler than water or brine and does not introduce internal stress that water or brine do. It also does not produce the hardness that water and brine can because of its slower cooling phase. Warm oil cools faster than cool oil because the viscosity is reduced and the oil is thinner, allowing it to cool quicker. Air quenching, see figure 11.8, is usually used on special alloys of tool steel such as A1s, A2s. And the A stands for air hardening.